Hi everyone, this is the second lecture of the second week and we're going to cover R-square. So once you fit the regression line to the data, we need a way to figure out whether the line is actually a good fit or not, or how good the fit is. There are three different ways of measuring this. The first is R-square, and R-square measures the fraction of variance in y that is explained by x. And it's unitless, but it ranges between 0 to 1. So 0 is when there's no fit versus 1 is a perfect fit. A related concept to this is called standard error of the regression. And this measures the magnitude of a typical regression residual in the units of y. And we'll talk more about that in this lecture. Another method of measuring the fit of the regression line is f-test, and this comes in handy in multiple regression lines, so we're not going to cover that in this lecture. And then the last way to measure the fit is to do a t-test on the slope, and we'll discuss that in the next lecture. So let's start off with discussing R-square. In the last lecture, we talked about fitting a regression line to the data points. So here we have all the data points or observations, and we want to fit a regression line that minimizes the distance between the regression line and each of these data points. What we have here, for instance, is that going back to our policy question of looking at the test scores and student-teacher ratio, we're fitting this line that predicts the average test score based on student-teacher ratio. And when we estimate the regression coefficient, we get this beta hat 0 and beta hat 1. Since we know, for instance, in I school district, say 4th school district, your student-teacher ratio is 50, say, then you plug that in to the x, and then you can predict what is average test score, and that would be this point. Yi is an actual data point. So even though your predicted test score is, say, 600, your actual test score is 620. So the difference, 20 score, test score, is actually U hat I, or OLS residual. This is something that is not explained by the regression line. As we have explained in the previous slide, the observed value y can be decomposed into what is explained by regression, y hat I, and what cannot be explained by regression, which is U hat I. When you take the sample variance of each of this term, you have a sample variance of y is equal to sample variance of y hat I plus sample variance of U hat I. So we call this total sum of squares. TSS is composed of what is explained plus what is not explained. So here we have explaining the same thing. So overall variability, or how much y varies, the actual observation varies, is composed of part that is explained by the regression, and there's a part that is not explained by the regression. So the formula for R-square is ESS over TSS. In other words, R-square is measuring how much of the total variation in y, or observed value, can be explained by the regression. R-squared equals 0 means that ESS is 0, meaning that the regression line doesn't really explain anything. R-squared equaling 1 means that ESS is TSS, which means that all the variation in y is explained by the regression variation. Usually, you never see R-squared equal to 0 or 1. It varies between 0 and 1. Closer the R-squared is to 1, means that regression line that you predicted is doing a good job explaining the actual data points. In a special case, when we have only one explanatory variable or one x instead of multiple x's in the regression line, we have this formula where r squared is actually equal to the square of correlation coefficient. This only applies in the case of when we have one single explanatory variable, which is a case that we are examining right now, where test score is explained by student-teacher ratio. You can see an example of that here. So here in the second graph, your correlation coefficient is negative 0.3, and your r squared is 0.09, which is the square of the negative 0.3. You can also see that as the r squared increases, here we have an r squared that is close to 1. You have data points that are basically on the straight line, that are very close to the straight line. And as the r squared gets smaller, for instance, if it's 0.25, the points or the data points are actually kind of spread out farther away from the linear line. I also want to emphasize to not put too much attention or too much focus on r-squared, because a lot of times in social science data, we don't have really high squares. So even though we can look at r-squares, in real life applications, we don't really focus that much on r-squared. Next, we're going to talk about standard error of the regression. Standard error of the regression, or SER, measures the spread of the distribution of U. In other words, it's measuring how spread out the data points are around the regression line. If you look at the formula of SCR, it almost looks like the sample standard deviation of OLS residual. So this part inside the square root looks like a variance of OLS residual, and then you're doing a square root. So it almost looks like a sample standard deviation, except for you're dividing by n-2. From here to the second line holds because by construction of OLS, when you take a sum of all the residuals, or when you actually take a mean of residuals, then it should equal 0. For more details on proof, you can look at the book in Stock and Watson. So intuitively speaking, SCR measures the average size of the OLS residual, or the average mistake made by the OLS regression line. So it's basically measuring how poorly the regression line is explaining the data points. Root mean squared error, or RMSE, is closely related to the SCR. If you look at the formula, it actually looks pretty similar, except for the only difference is that now you're dividing everything by 1 over n instead of 1 over n-2. This difference in dividing by 1 over n versus 1 over n-2 doesn't really matter as the sample size gets bigger. So if your sample size is 1,000, dividing by 1 over 1,000 or 1 over 998 doesn't really make that much of a difference. So RMSA becomes similar to SCR. Here's an output from Stata where we run regression of test score on STR. You may have seen this in the previous lecture. When you run the regression or regression command on Stata, it actually gives you R-squared and RMSE value, as well as the coefficient for beta 1 and beta 0. So what can we learn from the Stata output? The Stata output gave us the R-squared of 0.05, which is closer to 0 than 1. So we can say that the regression line explains 5% or very small fraction of the variation in Y. In this case, since our X variable is student-teacher ratio, we can say that the student-teacher ratio explains only a small fraction of the variation in test score, or our Y variable. We can also say that about 95% of actual data points are within 37.2 points of predicted test score. And how do we get this 37.2% or 37.2 points? Remember I said as the sample size gets larger, RMSE becomes similar to SCR, or there's no distinction. So let's assume that this is a large enough sample size, hence the RMSE that we got from this data output is equal to SCR. So SCR is 18.6. And we also said that SCR is sort of like a standard deviation. Using the empirical rule, which says that 95% of data points are within 2 times the standard deviation, that's how we're getting this number. So basically from the empirical rule, we're saying that 95% of the data points are 2 times standard deviation, which is SCR in this case, of the predicted test score.